Good day, ladies and gentlemen. Welcome back to another 5 Minutes with R. I'm Dr. Wee Kim Woo. Another request I received is how can we look into the observed and the predicted data of a graph and then try to compare them within a graph. So what does that mean? It means that if you have a model, we come up with a model and then we want to test the efficiency or the power of the model based on the observed data, and then we try to predict it and to check with the data to see whether the predicted data is it true or false. So one of the best example I can show you right now is by using this data simulation that I'm just extracted out. Like for example, over here, I have the third coral cover of a certain area in Malaysia, and I have a few types of fishes in the coral reefs, and then some other invertebrates or other animals in the coral reef. I have around 31 types of animals to compare with hard corals. So my idea is to what sort of animals that is affected by the increase and decrease of hard corals in the coral reefs. So if we want to run this model, we can really run the model using a general linear model with the Gaussian distribution and the identity family. And let me show you. If I were to run this summary for the full model, which means I use all the 31 animals to compare, you can see that not all animals has significant effect on the hard coral cover. So if I want to isolate some of those that are important when it comes to the interaction within the model, then I use a stepwise method. From this stepwise method, I isolate some more other organism out of it, and I only include those that are significant. When we look into this model, not all is significant as well. There are a few that is not significant, like for example, from Triton shell, giant clam, uh, trash fish nets, and also snappers did not show any significant difference as the p-value is more than 0.05. So I further isolate the data, and that I came down with a much leaner or slimmer model with only 1, 2, 3, 4, 5, 6, 7, 8 animals left out of 31 animals that I used to record with correlation with the hard coral cover. And with that said, with all these different types of levels or numbers of animals to uh, model it with a hard coral cover, I will have to recalculate back with the empirical or observed data of all the organisms related to the model to recalculate back the hard coral cover. So I use these models to predict the hard coral cover based on the simulated data. And when you see that at the end of this data set, I'll have the full data set and then the predicted hard coral cover. This is stepwise, and this is the slim fit model. As you can see, this doesn't really translate to exactly the same number as for the actual observed hard coral. So how are we going to evaluate the performance of the model? One thing is that we can set up the data next to each other, like here. So as you can see, this is the actual empirical data of the hard coral. This is the model for full model. This is stepwise, and this is the slim model prediction of the hard coral cover. The first thing we can do is to look into right here the AIC and BIC, the IKK indication criterion and the Bayesian. As you can see right here, the model stepwise has the lowest value for AIC, and at the other hand, the slim fit has the lowest BIC. Usually, if you want to check the performance of a model, the lower the AIC or BIC values, the better. So in this case, we can see that the fit is just slightly higher, 5 points higher than the stepwise, but a lot more lower than the stepwise when the slim fit compared to stepwise in BIC. And now since we have the value of the comparison between the hard coral and the the three other models. We want to correlate the data to see which one has the best correlation and also which one has the best uh, data spread or the narrowest data spread. So what we can do now is first you can also check the RMSE or the root mean square error. So root mean square error, the lower, the better. In this sense, which means the lower the value, the narrower the variation. As you can see for the full fit, yes, because it's overfitting, because of you have include all the uh, variables, and so you have overfitting issues whereby you have that is why your RMSE will be narrower than the rest of the model. However, in this case, it wasn't that much of a difference between all the three models. And if you were to look into the correlation by using this performance analytics, as you can see right here, that yeah, most of them showed a significant correlation with the empirical hard coral. However, is their value is moderate at best, and whereby the full model show the highest correlation as compared to the rest. As it goes down, the lesser the variables, the lesser the correlation of the prediction uh, models. And if you want to look into the density, the plot between the predicted value and the empirical value, we can also use the scatter plot of density, color density, or kernel density. For this full model, you can see that, yeah, everything hovers around here, and you can see how the data spread. And the blue one represent lesser data density, where the red one showed higher data density around here, which means most of the data concentrate here, and then the value is not exactly one to one, as it is a bit flat, uh, especially at the uh, fit the models whereby the value doesn't change as much as the empirical value. So if you look into the stepwise and also the slim model, you can see that in fact, the data is almost the same, whereby the full model seems to have more continuous data spread as compared to the others like stepwise and slim value, where it is narrower. However, there are also other outliers and spread out values all around here. So this is how you evaluate the performance of your model by a simple test. But there are other much complicated ones out there, and you can have a look or search it online. So if you find this video benefits to your work, please subscribe to this channel, share this video to any friends that will benefit to this. With that said, thank you.